All right, so let's get going on today's class. So just so we're absolutely clear on what is going to be on exam number one, last class was where the lecture portion of exam number one ended. So it's going to be chapter one in the readings, chapter four in the readings. It's going to be the lectures up until last lecture, and then it'll also be that chapter 7 section on effective studying. So we're going to keep moving on with cognitive psychology today by taking a look at a very important subsection of cognitive psychology, which is perception. But this will be on exam 2. So from here on in the lectures, this is exam 2 material. So just to be clear on that, chapter 3 perception will be appearing on exam 2. All right, so what are we going to be doing, taking a look at today? Well, we're going to take a look at perception. Perception is one of the sort of initial core areas of cognitive psychology. The more you become familiar with cognitive psychology, the more you will see that it is the dominant approach in just about any area of psychology now. But one of the first areas that it was applied to was perception, so it kind of becomes synonymous with that area. So we're going to focus today on what perception is. We're going to take a look in detail at top-down versus bottom-up processing, which was a huge debate in terms of perception. We're going to take a look at experience-dependent plasticity. So this kind of came up when we were talking about serial processing and parallel processing. Can your mind actually change in terms of how it processes information? And we'll see the answer is yes when we take a look at experience-dependent plasticity. And we'll apply that idea to an analysis of faces. And the question about whether or not faces are special stimuli that we have pre-made sensory processing mechanisms in our mind dedicated to faces, or on the other hand, are faces simply highly trained because we look at faces almost every day, all day. So are we just super familiar with faces, and that's why we're so good at processing faces? And we'll see how Gauthier et al. Try to answer that by taking a look at Greebles, and we'll see implications of that for our own behavior. So let's start off with the basics. What is perception? So perception is the experiences that we have that result from the stimulation of the senses. So it's very broad. It's a very general idea. You have an experience in your mind, and this is a result of stimulation of one of your senses. We're going to see that by far the sense that is most studied in psychology is vision. That is followed up by touch. That is followed up probably by taste, smell, and touch, then hearing, then taste and smell were the last ones. But definitely vision dominates the area. But don't remember that perception refers to anything: touch perception, taste perception, smell perception. But it's any experience that results from the stimulation of the senses. So we experience the presence of a rabbit in the external world. If that occurs from the stimulation of your senses, that is called perception. If you do not have stimulation of the senses, but you still have an experience, then that is what's known as a hallucination. So if you are experiencing things that are not there, so instead of seeing a regular rabbit, you're seeing a 7-foot-tall rabbit named Harvey, you are having a hallucination. So if it's not from the external stimulation of the senses, then we call that a hallucination, and that is a completely different area. But if you get it from stimulating the senses, then that falls into the realm of perception, which is what we'll be looking at for actually a couple of weeks. All right, so one of the things about perception that gives us a lot of insight about how it works is that perception can often be correct. So sometimes, in fact, most often, you see a rabbit in a field, turns out there's a rabbit in the field. Most times you see a chair that you want to sit down on, turns out the external reality is there's a chair that you want to sit down on. So usually our perceptions are correct, but they can also be incorrect. And this oftentimes gives us real insight into how our perception works. So one of the kind of basic principles of experimental psychology is that you oftentimes learn more from the errors than you do from when people do things correctly. So if you ever wonder why experiments are basically set up for you to fail, it's because as a psychologist, analyzing how you fail actually tells me more about what you're doing than analyzing your successes. So perception can be incorrect, and you'll see that a lot of work on perception is actually done with things like illusions here. So this is the Mueller-Lyer illusion. We saw this one before. And if you were to ask just about anybody whose perception is working correctly, which one of these lines looks longer, which one do you perceive as being longer, most people would indicate that this line here appears to be longer than this line here. But you've probably encountered this one before, and you won't be surprised that the two of them are exactly the same length. However, even that knowledge does not allow you to all of a sudden see the lines as being the same length. So you might be able, you'll know this ahead of time. You'll be like, oh yeah, that's a Mueller-Lyer illusion. They're the same length. But it looks like this one is longer. So your perception is incorrect, and that's an example of an illusion, something where the external reality of the situation does not match your internal experience. So your perception is not correct in the sense that your internal experience does not match the external reality. So the external reality is that these two are the same length. Your internal experience is that this one looks longer. That's incorrect. That's an illusion. Here's an example of a more elaborate illusion. So this is the road from the Abbey Road cover of the Beatles, but somebody has erected the Peanuts cartoon characters on it. And when you take a look at this, it looks pretty much as if somebody has taken cardboard cutouts, colored them in, and propped them up on this road, and then taken a photo, right? So it looks like this is upright, Lucy's upright, Charlie Brown's upright, Snoopy's upright, Woodstock is upright, Marcy is also upright, there he is. So this is the perception of three upright cartoon characters. This is actually the reality. So if we zoom in on this, you can see that this is what's known as an anamorphic painting. And what they've done is they have used properties of perspective projection, and they have drawn things that are closer to you, smaller, and they have drawn things on the road that are further away from you, larger in terms of the size on the road, so that when you see that stimulus, and there's a view from an upright view, but when you see that stimulus, your mind doesn't see the fact that these are really, really wide. Your mind takes into the information that the visual angle of this matches what is the visual angle that would occur if these images were upright. So your perception is of upright images, but in reality, this portion of Charlie Brown's head is far away. It's actually painted onto this part of the street, and it's super wide. But when you perceive it as being far away, the visual angle is less, so that it matches what would occur if Charlie Brown was standing up straight, and that's where that illusion comes from. All right, so that's the reality, that's the reality, that's the reality, that's what is externally there. However, our perception of this external reality gives us the experience of upright standing figures. That's our perception. Doesn't match the reality. That's an illusion. So far, so good? Alrighty. Okay, so this brings us to the idea of top-down versus bottom-up processing. It brings us to the idea of what are the processes that are going on in perception, how much of it is driven by the stimulus, and how much of it requires higher order processes like memory and rational thinking to influence the perception. So bottom-up processing is the approach or the idea that information for perception comes from the stimulus itself. Now you might notice that this is literally the definition of perception. Perception is the external stimulation of the senses basically the external stimulus itself. So in a way, everything about perception is bottom up. However, it's going to become clear that there is some information that is added to that. So psychologists have split that up into two kind of separate ideas. One is bottom-up processing, and that is just the information that is coming up from the stimulus. Just the fact that something is reflecting wavelengths of red, just the fact that something is giving you a certain visual angle, information that comes from the stimulus. And the stimulus in this case is what is referred to as the bottom. So bottom-up processing, you can think of it as almost unconscious. You're not thinking about it. Your mind isn't doing anything with it. It's just coming up directly from the stimulus. So an example of bottom-up processing would be this image right here. So to know that there are 1, 2, 3, 4 things there is an example of bottom-up processing, right? To label them as horses requires some top-down processing. We're going to get to that in a minute. But to just know that there's 1, 2, 3, 4 things there is bottom-up processing. To know that they are different colors, so that there's a difference between this color and this color, difference between that color and that color, that's bottom-up processing. That comes from the stimulus itself. So there's information in this picture that comes from the picture itself that can lead you to perceive what is going on in this picture. Another way to think about it, if you showed this to a person who had never seen a horse, had never seen brown, had never seen white, and had never seen black, they would still be able to take a look at this picture and say, oh yeah, there are 4 things there, and they are different colors. I don't know what those things are called, and I don't know what those colors are, but I can see these 4 different things, and I can see that they're different colors. So bottom-up processing is the processing that comes from the stimulus, and then you can think of your perceptions being near the top, comes from the stimulus, works its way up, and you get a perception. Top-down processing is the opposite type of procedure. It's the opposite sort of process, and it's the information for perception that comes from higher level knowledge. So things like memory, things like reasoning, things like previous experience. All of that is a top-down, knowledge of your culture. All of that is kind of a top-down processing system that gets added to whatever that external stimulation is. So top-down processing, that general knowledge is considered the top. And this is where knowing information can actually change your perception of a stimulus, right? So unlike the Mueller-Lyer illusion, where knowing that they're the same length didn't change your perception of the 2 lengths of lines, occasionally knowing something and having prior knowledge about it can help you change your perceptual experience for the same stimulus. And there's a lot of examples of this. One of the more famous ones is this example here. So take a look at this image and see if you can find a face, see if you can find a person. Has everybody found a person? All right, how many people see a young woman? Show of hands. How many people see an elderly woman? Show your hands. All right, about half and half. So we'll start off with the we'll start off with the young woman. So is anybody not able to see a young woman? All right, a couple of people don't see a young woman. This is an unambiguous image of the young woman. So in this image over here, the young woman, she's looking away. That's her eyelash. That's her nose. That's her ear. This is a little choker necklace that she's wearing. This is her jawline right here. So she's kind of like doing this in this image. No. Still no? Let's try that some more. Hmm? So this isn't the mouth. That's a necklace. That's an ear. This is an eyelash. This is the nose of the younger lady. Okay, so now you got it. Okay? That is an example of top-down processing, right? First, when you looked at this stimulus, you saw an old woman. Now, with that additional information, with that additional higher level cognition coming down from the top, where I told you, this is an ear, this is an eyelash, this is a nose, you used your knowledge of human anatomy, and you said, all right, I know where eyelashes and ears and noses are supposed to be. Oh, okay, now I can see it. Now I see that young woman. We take that same stimulus, and for anybody, can anybody not see the old lady? The elderly woman? All right, so we won't get a nice example of top down here. But there's there's an unambiguous version of the elderly woman there. So we got the mouth there, we got the chin here, we got the nose right here. That's one eye, that's the eyelash of another eye. That is the bags under her eyes. And again, it's the exact same stimulus, right? This is the exact same stimulus for the young woman and for the old woman. But depending upon your top-down processing, depending upon your the knowledge that you're bringing down to it, you can change your perception and see it, experience it as a younger lady, or experience it as, you know, an elderly woman. So that's an example of top-down processing. And one of the big debates that was raging in perception, especially in the early goings, it's kind of died down a little bit as people have gained more knowledge about this, but it's still an issue to kind of determine, is we know that bottom-up processing has to be involved in perception, because your experience comes from the external world, comes from the external stimuli. So at least part of it is driven by that external stimulus, right? So I cannot make this look like a male deer, right? I can't make this look like, you know, a buck in the forest, right? No matter what top-down processing I do. So part of it has to be bottom-up because, again, it comes from the external world. But there's also evidence that part of your perception is also top-down, and we just saw that. You can see it as a young lady, you can see it as an elderly woman. The stimulus itself hasn't changed, so the bottom-up portion of it is exactly the same. So the fact that you can switch your perception from one to the other means that there has to be some top-down processing that is going on here. The question then becomes, how much of perception is bottom-up and how much of it is actually top-down? How do these two processes interact? Which one is more, which one basically carries the weight of actually producing an experience? How much of perception is top-down or bottom-up? And then also, how do these two things interact? You know, is it mostly top-down, where there's very little input from the stimulus and everything is ambiguous, and without some sort of knowledge that you can take from the world, you would never be able to perceive anything? On the other hand, is it mostly bottom-up, in the sense that most of the experiences that we have come directly from the stimulus, and there's only a little bit that is influenced by top-down processes? How do these two interact? So let's take a look at a couple more examples before we sort of ask, when is it going to be mostly top-down and when is it going to be mostly bottom-up? All right, so this is example number one. So does anybody know what it is that this is a picture of? So this is a picture of an object. It's a picture of a thing that you have all had a lot of experience with. So when you recognize what it is, just raise your hand. Just raise your hand. All right, we got one. Okay, so at this point, this is all bottom-up processing, right? At this point, you're taking into account, this is a big stimulus, big white area. We got a couple of small black triangles in there. And you're bottom-up processing, you haven't been able to identify what this is yet. I'll give you the title of this. This is called the Big N. How many people can see it now?
That's what I was thinking.
Yeah. Yep. So this is the Big N, and if you still can't see it, it's just a very thick, bold white N. So there's the top, there's the line up there. So all your cognitive demons are basically super confused right now, but there's again, the first part, second part, third part of the N. So this is a big N. And this is an example of, well, which kind of processing is this? If you have to say your ability to see this as an N, is it mostly due to bottom up or is it mostly due to top down?
Bottom down.
Exactly. This is an example, a very clear example, where it's mostly due to top down. Because when it was just bottom up information, just the stimulus information, very few hands went up. But as soon as I said, oh, let me give you another piece of knowledge, apply your knowledge of the alphabet to this, this is an N, all of a sudden everybody was like, oh, there it is. I can see it now. I'm perceiving it, as this N. So in this case, this is mostly the perception of this successfully as the big N has mostly to do with top-down processing. Because without the top-down processing, you typically are not able to see the N. All right, let's take a look at another example here. So we got this picture right here. And in this case, you can perceive, how many people perceive the pencil as being either bent or broken? Okay. Anybody who didn't put up their hands, your vision's not working correct. And you should go see an eye doctor. We know the pencil's straight, right? We've all seen this trick before. We know the pencil is straight. But how many of you see it as having a broken portion to the pencil? All right, that makes me feel better. So no need to visit the eye doctors. Okay, so your experience, your internal experience of that external reality is incorrect in this way. Your internal experience is of this bent pencil, but we know the external reality is of an actual straight, unbroken pencil. So let me give you a little bit of top-down information. Yep.
I have a quick question.
Yep.
Isn't the external reality that the image of the pencil is distorted because of the distortion of the light molecules going through the water?
Exactly.
So isn't that the reality, not that? So like we're still experiencing the reality because we know that that image is distorted. The reality is that viewing that image will always be distorted because it's in water.
That is a good kind of question in terms of, and this is something that actually comes up in my research a lot. Where do you define that external break between what's internal and what's external?
Mm-hmm.
Because on the one hand, the external reality of this is that the pencil is not broken.
Yes.
On the other hand, the external reality of this is that the light reaching your eye
Mm-hmm.
is indicating a shift in the pencil.
Mm-hmm.
So my sort of reason for including this example is that if you define it as the external pencil is solid,
Mm-hmm.
but it looks bent, you can know everything that you just said about light refraction.
Mm-hmm.
You could say things like, well, light travels through a medium, and air has a lower refractory index than water does, and because of that, when the light is reflecting from here, it's going to get skewed this way, it's going to get skewed that way.
Mm-hmm.
You could take a physics professor, show them this image, and they will still see it as being that broken line. So in that case, this is an example of bottom-up processing, because all of your knowledge of how light works, how water works, how refraction works, even if you're like the world's leading expert, you still cannot top-down process enough to make that pencil look like it's straight.
I understand now. Thank you.
And it's actually you're asking a very good question, a very difficult question, because in my own work, I deal with metaphoric information in pictures. And as we're going to see, one of the definitions of whether something in a picture is metaphorical or not is whether or not it happens in the real world. So if something happens in the real world and you represent that thing in a picture, that's a literal representation. If something doesn't happen in the real world and you represent that thing in a picture, that is a metaphorical representation. So gigantic size is a very clear example of that, right? Somebody might be a very important person, but that doesn't make them 20 foot tall. But that's what we understand, that it's a metaphorical symbol of this person's power and importance. The place where I get into this kind of discussion with other people has to do with multiple images. Because when you run, when you have, let's say that you're running or you're moving very quickly, you're not going to break up into multiples of yourself. I have never run so fast that copies of me started popping up behind me. So externally, there's not going to be multiples of you. But if you ever do this in front of your face, you will see that there are a couple of images of your hands, especially at the end points. So externally, you're kind of experiencing this, oh yeah, there's multiples in the world. So I've still not come up with a good answer to whether or not multiples would actually count as metaphorical or count as literal, because of this exact same question of where do you draw the line. But if you draw the line at this pencil is not broken, but we see it as broken, then this is clearly, number one, an illusion, and also something that cannot be fixed with top-down processing, indicating that bottom-up approach. All right. Let's take a look at one last example. So here we have an image by Bev Doolittle. And let me zoom in on that. Okay. So my question is, how many horses?
5.
All right. Hands up if you can see 3 horses. Hands up if you got only 3 horses. Let's see that. Only 3? 4? How many see 5? How many see 6? Okay. I don't think there's 6. Wait a second.
Yeah, I was like, there's 5.
1, 2, 3, 4. Nope, there's only 5. All right. Does anybody? Okay. So this is a nice example where people are like, oh, the other one is over here. The other one is over here. So here's horse number 1. We got a little horse face right there. Here's horse number 2. We got horse number 3 down here. We got horse number 4 over here. And then we finally got the horse number 5 over here. So this is an example that's very difficult. I mean, this artist, that's her sort of modus operandi. She makes these paintings where it's very difficult to see because the figure kind of blends into the background. But here we have 5 different horses, and you could probably see many of them right off the bat, right? So nobody was like, what are you talking about? Horses? I don't see any horses. There's no horses. Most of us could see, 1, 2, 3 horses rather easily. If you couldn't see, though, all 5 horses, by the time I finish saying, well, here's one face, here's another face, third face, fourth face, and fifth face, by that time you could say, oh, I see it now. I have the internal experience of there's 5 horses. So this is a nice example where there seems to be a large interaction between the 2 processes. There seems to be a lot of bottom-up processing going on. A lot of this is driven by the stimulus itself. But at the same time, you get a lot of help in this picture by top-down processes. If you cannot see all 5 horses, it's very helpful for somebody to say, well, there's one right there. At which point your knowledge of horses, your knowledge that they usually don't have floating severed heads in our world, will allow you to be like, oh, right, and there are the legs. Okay, I get it. There's the horse. So the question we're going to ask right now is, when is it, or why are some stimuli mostly bottom up? Why are some stimuli mostly top down? And why are some sort of in between? So what are your ideas about things that these images differ on? That would make this one here mostly bottom up. It would make this one here almost exclusively top down. But this one here really need an interplay between the 2 in order to be perceived. Any ideas? Mm-hmm.
Well, if you don't know what an N looks like, you're never going to get the one on the right.
Yes.
If you don't have the general knowledge of what an N looks like, then you're just going to see a white box with things in it.
So why is it that the knowledge, though, is required for this one? Why do you think you need to do that? Whereas when I showed you I wonder if I have an N in this at all. Oh, there we go, top down. All right, when I showed you this, I didn't have to point this out to anybody and say, that's an N, by the way, right? Where people are like, top jow, what's top jow? It's like, oh, that's an N. Oh, I get it. Why is it that this N is completely recognizable? This N, we need that top-down processing. But for this, top-down processing doesn't do anything. It's mostly bottom-up. Ideas?
Because like it's not what a typical N looks like, so it doesn't fit like our idea of what N should be.
All right, so it's not typical of what an N usually looks like. Now it does fit into what an N does look like. So when it's explained to you, it does fit into it, but it's not typical. So you're on the right track. What's another way of saying that it's not typical?
That it doesn't like mimic external reality like that we see all the time, I guess.
It doesn't mimic external reality. So all of this is kind of getting to the point that it is extremely ambiguous. So this stimulus over here, and it was mentioned also before, if you don't know what an N is, this could just be a white background with, black triangles. This could be a number of different things, right? It's ambiguous. Is it a wall? Is this the figure and this the ground, or is that the figure and is this the ground? It's very ambiguous. And what you'll find if you go into perception is that a lot of evidence for top-down processing comes from these ambiguous stimuli. So things like the big N, things like the elderly woman versus the young lady, right? Those are stimuli that can be taken two ways. They're very ambiguous. They can go one way or the other. So those are the ones where top-down processing becomes very, very important. On the other hand, this one here is very unambiguous, right? It's got a lot of information. It's very realistic. It's clearly a glass, clearly water, clearly pencil. Nobody had to ask me what they were looking at in this one. I didn't have to point out, well, there's a pencil right there. There's your glass right there. So when it's unambiguous, when it's clearly defined, and something that we regularly encounter in our real world, those seem to be mostly bottom up. And then in specialized cases like this one here, you get a real interplay between bottom up and top down processing, because this is a very realistic picture, but it's also set up in a way that makes it very ambiguous. So there's a lot of information here for the horses, but it's hidden and it's ambiguous because it matches the information for the rocks and the snow. So because of that, bottom-up processing can do a lot because it's got a lot of information to work with, but top-down processing has to come in because it has to resolve a lot of those ambiguities. So if you pursue perception in psychology, you'll find this debate rages where people are, no, it's mostly top-down, no, it's mostly bottom-up. And what you'll find is a big, huge commonality is that top-down processing is oftentimes most important when your stimulus is ambiguous. Bottom-up processing is oftentimes most important when your stimulus has enough information to not be ambiguous. And as we're going to see when we take a look at ecological psychology, usually when you're in your own environment, your stimuli are very unambiguous. They're specified, and a lot of perception seems to be bottom-up processing. All right, any questions about top-down, bottom-up? All right. So now let's move on to the next topic, which is experience-dependent plasticity. So an experience-dependent plasticity, this is a mechanism that our minds have, and it is where your structure of your brain is actually changed by experiences. So this is going into a little bit of that third level of Mars tri-level hypothesis, which is how is this thing implemented. So experience-dependent plasticity is some mechanism that our brain has, is some mechanism that our mind has. We get better as processing things. The more we experience them, the more we practice them. But this experience-dependent plasticity is also shows up in your actual brain structure, because your brain structure will change by experience. So depending upon your how much you practice something, how much you experience something, your actual neurons in your brain and structure of your brain will change depending upon that experience. So your brain is plastic. It can change, but it depends upon having that experience. So one of the areas where this was very intensively studied is called the fusiform face area, or FFA. And this is an area in the human temporal lobe. So it's right about there. And this is an area that is believed to be specialized to respond to faces. So if you put somebody into a fMRI machine and you show them a face, this area will absolutely light up. If you show them something that isn't a face, this area will not light up. So it's been implicated in perception of faces. It seems to be specialized, responding only to faces. And the question is, in terms of the fusiform face area, is this area just for faces? So is this a special area of your brain that has been pre-programmed to respond to faces? The same way your occipital lobe over here is pre-programmed for visual stimuli, is this area of the brain just something that's been pre-programmed to respond to faces, or is this an area that is for very highly trained stimuli? And it lights up to faces because faces is one of the stimuli that everybody is highly trained on. So again, if you just kind of monitor your experience for a day, think about how many times you see faces during the day. I mean, when I work here at IUSB, I get 30 odd examples of faces every hour and 15 minutes where I'm just being bombarded with that stimuli. I get very, very practiced at looking at faces. When you think about how often you talk to somebody, right, you look at their face. It's very distracting to talk to somebody and not look at their face. Think about the time you spend getting ready in the mirror every morning, right, processing faces. So it could be that this area lights up just because it's for highly, highly trained stimuli, or it could be because it's an area that's specialized for faces. Mm-hmm.
Do they know that, because don't babies recognize, isn't it like one of the first things they can do is recognize faces? Like, well, relatively soon.
One of the first things that babies do is, they do look at faces more often. So there is a component of faces that is, we'll use the terminology before, exogenous control. There's something about the face stimuli that does attract babies' views. I do not recall if they've, how young they've ever seen brain images of babies. So it would be very interesting to know if you could actually see activation of this fusiform face area in babies. That would be a good indication that yes, it is actually predisposed, pre-programmed for faces. Mm-hmm.
You know if it's just human faces that this area of the brain responds to, or is it anything that has a face, like animals?
We are going to get to that in just a moment. But that is one of the questions. So is it just for human faces, specialized for human faces, or is it for other faces, or is it for other trained stimuli? So is it for other things that you can become trained on? So let's take a look at how they attempted to answer this question. And one very influential experiment that took a look at this was by Gauthier et al. Back in 1999. And they had people try to identify what they called Greebles. So they made these stimuli here. So that's a Greeble right there. That's another Greeble right there. There's a third Greeble right there. So these are Greebles. And they had subjects try to identify these Greebles. And these Greebles could be categorized by either by a combination of the family they belong to and the gender that they had. So the families, there was, it looks like a Panar family, there's a Gaz family, there's a Radix family, there's a Tasso family, I can't make that one out. And then there is a Glee gender and a Plock gender. All right, so all of these Greebles came from certain families. All of these Greebles had certain genders. And what they would do is they would train subjects on these Greebles. So they would show them something like this, and they would say, what do you think that Greeble is? And they would say, oh, is that a flock radic? And they'd be like, no, that's a glee Tatar. And they'd be like, oh, okay. And then they would show them this one, and they would be like, what is that? And they'd be like, oh, is that a tasso? Is that a glee tasso? And they'd be like, no, that's a glee gaz. They'd be like, all right. And they would do this over and over and over and over again to the point where they would show them a Greeble, and they would be like, what's that? And they'd be like, oh, that's a flock tasso. And they'd be like, yes, it is. That is a flock tasso. So these people, these subjects, became experts on recognizing Greebles. Right? The same kind of way that people that play Pokemon become experts on every single evolutionary stage of all, I don't know how many they have now, but the same way they can identify those, they can identify these Greebles. So you can imagine it took a lot of training before you could take a look at this and say, oh yeah, I know the family and the gender of that particular Greeble. So what they did though, to kind of answer this, is it for faces, fusiform face area, is it for faces or is it for just highly trained stimuli? What they did was they took scans of the brain's activity before they were trained on these Greebles and after they were trained on these Greebles. So they would have them do this task, take a look at this Greeble, what is it? And they scanned their brains before they got trained, basically when they couldn't recognize the Greebles, and then after they got trained, when these subjects could recognize the Greebles. And what they found was that before training, there was very little response to the Greebles in the fusiform face area. So we'll zoom in on the top part here on the brain scan. So here we have the fusiform face area, and you can see that it's lit up there for faces. So the whiter the node here, the higher the activation, the gray areas, no activation whatsoever. So we see a large activation here in the fusiform face area when the faces were presented, but when they presented Greebles, no activation whatsoever. They were just sitting there like, no, I don't see anything. So high activation versus no activation. And when we take a look at the graph, we have your fusiform face area response, and then we have the responses before training for faces and for Greebles. And you can see that the response for faces is massive. The response for Greebles, hardly any response. So this is not surprising. The before training aspect of this is not surprising because it is well known that the fusiform face area responds to faces. So they were establishing here that before training, this fusiform face area responds to faces. So all the subjects are, their fusiform face area is lighting up. But to the Greebles before training, that fusiform face area is not being used at all. All right, so that was before training. So then what they did is they went through that extensive training process and took a look at what happened to this fusiform face area after they were trained. And the idea was that if the fusiform face area is specialized for faces and only for faces, then after training, we should still see this pattern of results over here. On the other hand, if the fusiform face area is just for trained stimuli, for highly trained stimuli, the fusiform face, the face area can go through experience-dependent plasticity, then after training thousands of trials on these Greebles, we would expect that the activation of the fusiform face area would increase for Greebles, right? So that's a question here. If it's just for faces, we should see no change after training in how much Greebles activate this area. If there is, if it's not just for faces, but for experienced stimuli, we should see an increase. So what did they actually find? Well, they found that increase. They found that when they showed these trained observers, once they could identify Greebles, when they showed them these Greebles, there was actually a large response to the in the fusiform face area for these Greebles. So this is before training, and that's what happened after training in this experiment. Yep.
Why did the FFA response for like human faces go down after training?
So this here has to, so the fact that it went down after training, that has more to do with the way that they define these measures, rather than whether the training actually went down.
Oh.
So one of the things that, and I'm not an expert in neuropsychology, but one of the kind of principles that I know is that when you do these scans of your brain, it makes it look like the rest of your brain is asleep. It's not. It's your entire brain is activated the entire time. So that idea that, oh, we only use 10% of our brain is ridiculous. We use like 98% of our brain all the time. What they do, though, is they do this difference analysis technique where they will show you a face, and then they will show you a stimulus that's different, not a face, but still, something that you're looking at. And then they'll subtract the activation for those two, so that everything that your brain is doing to perceive things is subtracted from the two. Everything that your brain is doing to keep you alive, like breathe, is subtracted from the two. So the only difference left is whatever is different about the stimuli. And in this case, that's why this certain area lights up. The only thing I can imagine for this is it has something to do with the fact that the differences between faces and Greebles was not as large, so it kind of brought it down a bit. So it's not that you can see here, the activation, let's zoom in on the activation here. You can see that the face activation in the fusiform face area is still going crazy. But now, this is before training. We can see from the time before training, there was nothing for the Greebles. Now, after training, there is for the Greebles, but there's still activation in the fusiform face area. So importantly, before training, no activation in the fusiform face area for the Greebles. After training, we start to get activation for the fusiform face area. And it's not as much as we get for human faces, but the fact that it's anything at all after just what really is a minimal amount of training in identifying Greebles is kind of astonishing. That even with that little bit of training, it was thousands of trials, but I get thousands of trials of faces every single day. But even after just a few days of thousands of trials, we get that activation in the fusiform face area for Greebles, indicating that experience-dependent plasticity. All right, and importantly, also for another measure of the fusiform face area response, this is what it was like before training. You can see highly responsive for the faces, not so responsive for the Greebles. After changing, evidence of experience-dependent plasticity, where the activation of the area for Greebles increased substantially. And again, there you have the side-by-side. So that training on the Greebles seems to have changed the activation of the fusiform face area, seems to have increased it, indicating, number one, experience-dependent plasticity. So the structure of that fusiform face area actually changed. Those connections were actually rewritten to help them recognize Greebles. And at the same time, it also argues that this area is not specialized for faces. It's specialized for highly, highly trained stimuli. All right, any questions, comments? All right. So the conclusion from the Greebles was that the fusiform face area responds to faces, and it responds to other complex stimuli as well. And there is also converging evidence for this. So this was brought up before. There's also converging evidence for this from other types of investigations where they took a look at the brains of car experts, right? So they took a look at the brains of people who, as soon as they see a car, they'd be like, oh, that's the 1969, Dodge Charger with the built-in 4-quad Ram, whatever. They can immediately identify it, right? As opposed to a lot of us when they're like, well, what kind of car is that? And you're like, oh, it's a blue car, right? So cars for car experts activate the fusiform face area. Birds for bird experts also activate the fusiform face area. So if you're one of those, avid bird watchers and you're trying to have your big year, when you see a bird, your fusiform face area will start lighting up. So again, your fusiform face area will not light up if you see a bird and you're like, well, that's a big bird or that's a black bird. But it will light up if you're like, oh, that's a southwestern fruit-tailed raven, right? That's when your fusiform face area seems to be involved. So this looks like, again, kind of clear conclusion from both the Greeble experiments and the CARs for car experts, birds for bird experts, that the fusiform face area seems to respond to faces, but also to other complex stimuli as well, just depending upon getting enough practice. So you practice Greebles, FFA responds to Greebles. You're a car expert, you've been looking at thousands and thousands of cars, FFA responds to cars. You're a bird expert, you've learned to identify all these different birds, FFA responds to birds. So this is not completely accepted, however. It's not completely accepted that the fusiform face area is used for just complex stimuli in general. And one of the challenges to this, well, does anybody have any idea what might be one of the reasons why people will still say, well, we're not convinced that the fusiform face area isn't just for faces, even after evidence like this? All right. Well, let's take a look. What are the challenges? Well, one of the challenges is that it might be that the fusiform face area gets lit up, not just for human faces, but for things that look like faces, right? So it might not just be for human faces, it might be for things that look like faces. And if you take a look at, we mentioned babies before, if you take a look at babies, one of the stimuli that is extremely, babies respond to a lot, is just this. Right? And this is all colored in. And it's a high contrast black and white thing. It kind of looks spooky. Anyways, that's what they respond to. Now, that does not look like a face at all, right? If I told you, oh, I took a picture, of somebody, and I showed you this, you'd be like, that's not a picture. That doesn't look like a face. But we recognize this as a face. So it could be that the fusiform face area responds to things that we recognize as faces, that are face-like, not necessarily just defined for a human face, but things that are face-like, things that have the correct configuration in order to be classified as being face-like.
Cars?
Exactly. So we'll start off with the challenges for the Greebles. Some of these Greebles actually look like faces, right? So we got this Greeble right here, and it's not that hard to see the face. You just put some googly eyes on it so you know where it's at. You can see it. It's right there. It has hair, right, up here. It's got a nose right here. This structure here is very face-like, and it's basic, right? It's even got the right sort of contours, where this is like your jawline. So it could be that the area that got lit up, that fusiform face area, showed that activation because many of the Greebles, not all of them, but many of the Greebles had that basic face structure. And the learning process basically allowed these individuals to notice that face structure, see that face structure, and as soon as you see something as a face, that might be when the fusiform face area gets activated. So it could be that their ability to see the Greebles actually piggybacked on their facial processors. So they were able to recognize them by basically realizing that, oh, that's kind of like a face. Then it activates your fusiform face area, and then things are more easy to recognize. So this change here might have only to do not with any of the experience other than recognizing the faces in the Greebles, and then the fact that it's not as high as human faces could be accounted for by just realizing that not all of the Greebles had face-like features. So there were Greebles that you wouldn't be able to find a face on, and that might be why we have this little dip here in terms of the activation. All right, so car experts were brought up. And you might say, well, what about the car experts, right? Because they're looking at cars. Do cars have faces? We're going to see that, yes, they do. Everything has faces. So we got a face right here. So we got eyes right there. We got a nose right there. We got a mouth right there. This is a very happy car, right? We take a look at it and we're like, oh yeah, there's a face, there's a happy car. We know that this car is also happy, right? So if I ask you to identify the emotion of this car looks happy. Does this car look happy? No, it does not, right? This car looks really worried, actually. So the fact that you can see the face-like things in these, the face-like structure in these cars might be why car experts light up their fusiform face area whenever they see cars. And you might say, well, why doesn't this work for everybody? Why is it not everybody, when they see this? Because I don't know how many car experts are in here. I am not. But I can see this as a sad face. So why is it that my fusiform face area might not light up as much when I take a look at cars? Well, it's because I might take a look at a car like this, and I might not be able to see a face, right? So not all cars are readily apparent where the faces are. Can anybody see the face on this one? We got a couple yes, couple no's. Face is right there. All right. So I couldn't see that face initially, right? When I saw this car, I couldn't see that face. But a car expert might, right? After experience, much like the Greebles, where at first they didn't look like faces, but then later they're like, ooh, I can see the face structure there. Maybe one of the reasons that car experts get so good at recognizing cars is because they're able to see the face-like things in certain cars, and that allows them to not only be more experts in terms of identifying it, but that also makes their fusiform face area light up.
So in theory, a car expert, if they can see faces in cars and differentiate cars, would they be better equipped to differentiate faces? My husband's a car expert, and he can't remember faces for the life of him.
I would say no.
Okay.
That would probably not be the case because it seems like the fusiform face area is highly trained for complex, could be highly trained for complex stimuli, but there's no reason to think that that would transfer.
Okay.
And if you are noticing the faces in cars, I don't think that would at all improve your recognition of faces in general.
Okay.
Yep. All right, so those are the car experts. What about the bird experts? Well, should be no surprise here. Birds have faces, right? And as much as bird faces are human-like, have the human-like structure, as much as they have two eyes over a nose that kind of goes into a mouth, there's very, like I said, there's very little that is required in order for something to look like a face. We got a face right there. We got what looks like an angry owl there. We got a very angry, ostrich right there. So again, faces everywhere. So it's not that surprising that a bird expert who might have become more attuned to where they need to look to identify certain birds, maybe they spend more time looking at the faces of birds rather than what I would look at. Typically, I look at the wingspan, and I'm like, oh, I wonder what that is. Maybe they just look at birds in their faces more, and that's why that fusiform face area lights up more. And then there have been other studies that have taken a look at other complex stimuli and have found evidence that just in general, some very complex but highly trained stimuli tend to activate the fusiform face area. But we're going to see in a few examples that there is this concept known as pareidolia, and that is a tendency for us to see and impose order on chaos. So when we perceive something in the external world, we like to put our structure on it, and oftentimes that leads us to see things that aren't there. So these are all going to be examples of this phenomenon, and it is massively strong with faces. So, we got candle holders right here that look like a line of individuals just shrieking in terror, right? They just saw something and they are scared, right? That's not what this is. But very little structure is required before your fusiform face area, or before a face is perceived. We got a rather happy set of binoculars or telescope here. We have a kind of worried faucet, right? Complex stimuli, but again, there's your face. We got a chair that just can't wait for you to sit down on it, right? This is one I think that we've all noticed. The plugs look like rather shocked individuals. And again, it doesn't take much, right? Just two dark areas over one dark area, and it triggers faces, which could light up our fusiform face area. There's a face right here. There's actually two faces. So you can see how very complex kind of arrangements that have no faces in them whatsoever can be easily seen by us as having faces. So just random assortments of birds, hats that have, you know, laces and eyes, and even people who have faces can have other faces. So this is Iggy Pop right there. That was a meme. Sad torso is sad. There's a face right there. So if you were to train people on any complex stimulus, and they were, yeah, usually people don't want to look at that one for too long. If you were to train people on any complex stimulus, and you notice this fusiform face area started to get activated after training, the question is always, is it because these complex stimuli are highly trained, or is it now because the faces are being seen in this complex stimuli? And as we've seen, faces are like everywhere. There's so many examples of faces in our stimuli that if you have a set of stimuli like the Greebles, you know, like the 80 Greebles that they made, chances are that 20, 30, 40 of them might have a face-like structure, and once that gets picked up, it could light up your fusiform face area and then kind of make it seem like it's for highly trained stimuli, while it's still only for the for faces. All right, so challenges. So if you wanted to show that the fusiform face area is for faces only, if you wanted to, evidence that would point in that direction would be if you can show that the fusiform face area responds to faces, which it already does, so we already know that, and it also responds to untrained faces. Then it would show that it is not for highly trained stimuli, it is for faces. So it's not the fact that, you know, your typical human face is highly trained that it's making the fusiform face area respond, is that any face will make any human face will make the fusiform face area respond, whether it's trained faces or, and I put that in quotes, untrained faces. Because what would untrained faces be like? Well, one possibility is, and we see this a little bit in interracial identification phenomenon. So you are, regardless of what race you are at a deficit when you're trying to identify people outside of your race, and you are at a benefit when you're trying to identify people inside of your race. And there's many explanations for this in terms of, how diverse people's groups are, how much they interact with people of other races, and just the fact that it doesn't matter how diverse your circle of friends are, you are still going to interact with faces of your own race to a larger amount. If you live with your family and they are the same race as you, and B, if you look in the mirror. So I could hang out with as diverse a range of people as possible, but my main facial experience, my highest facial experience, would still be of a Caucasian male, because I got to get ready in the morning. This doesn't just happen. And, I spend time looking at the mirror. So, anyways. So, we would need to show it for untrained faces as well. And we would need to show that the fusiform face area does not respond to trained complex objects that lack faceness. So this would be a real challenge, to come up with trained complex stimuli, none of which have that facial quality. So take a look at cars, get rid of all the cars that might have faces. Take a look at houses, get rid of all the houses that might have faces in them. as you can see, just from the example that we saw, that would be massively difficult to do. But that is the kind of thing that would need to be done in order to show that it does not respond to trained complex objects. Train people on a complex object that has no faceness in it, and if the fusiform face area does not respond to that, that's a good indication that it's for faces only. If you wanted to show on the other hand, or if you were trying to determine on the other hand, is it for complex stimuli, then you need to show that it does respond to trained complex stimuli that lack faceness. So if you could come up with, and if you can come up with it, let me know, and we'll see if we can put this issue to rest. If you can come up with something that is complex, some stimuli that is complicated, like the Greebles, none of which have faceness, none of which have this sort of configuration anywhere in their, in their stimuli, and you can show after training that the FFA responds to them, then you would have a very strong argument that it is for trained stimuli because none of these have that idea of faceness. All right, any final questions, comments, observations? All right, so that is it for today. For next class, we are having the exam. We're going to be doing it in here. All you're going to need is a pencil. And if you're feeling frisky, don't bring an eraser, but also, bring yourself an eraser just as a backup. But that's all we're going to be doing next class. So I will see you here. Make sure that you finish up any of the homework assignments. So there were still some issues with students missing homework assignments. I extended that deadline. It's midnight tomorrow night, so make sure that you finish up anything that you might have missed. Make sure that you're doing your mastery practicing. That is going to be due Monday at midnight, so the day before the exam, in order to help you prepare. Other than that, we are done for the day.